Power. It would be great to be powerful, to have the power to do something fantastic. The everyday use of the word power brings many different things to mind. Someone in control of others, governments, nuclear weapons, the electrical power supply. All these ideas are correct and appropriate, but, as we'll see in physics, power has a very specific meaning. Weightlifters are powerful. They lift heavy weights above their heads, hold the bar steady until the judges are satisfied, and then return them to the ground. Weightlifting is a speed sport. The winner of a competition has to lift the greatest weight over the shortest period of time. This ties in nicely to the definition of power in physics. Power is defined as the rate of doing work. We can write this as an equation. P for power is equal to W for work divided by T, the time taken. Work is measured in joules and time in seconds. Power is measured in watts. 1 watt is the power that is required to do 1 joule of work on an object in 1 second. Let's go back to the weightlifter. Lasha Talatskadze of Georgia set a new world record in 2017 when he lifted 217 kilograms above his head to an approximate height of 1,5 meters. It took him only 1,2 seconds to do this. What average power did this man output? Power is equal to the rate at which work is done. The work done is equal to the force applied times the displacement times the cosine of the angle between the force and the displacement. Let's assume that he lifted the weight vertically off the ground. The angle between the force and the displacement is 0 because they're both in the same direction. The work done is equal to the force applied times displacement. Let's make another assumption. Let the force applied be equal to the weight of the bar. These assumptions will help us calculate the minimum power that he exerted on the bar. Power is equal to the force applied times the height divided by the time. The work done is equal to the weight, 217 times 9,8 times the displacement, 1,5. The time taken is 1,2 seconds. His power is 2,658,25 watts. That's a huge amount. How does this compare to the average power of a horse? Years ago, before motor vehicles were invented, people travelled by horse-drawn carts. To compare the power of steam engines with something people were familiar with, James Watt and other physicists defined the unit of power as the horsepower. It was a measurement of the power that one horse could develop when pulling a weight through a height. 1 horsepower is equal to 746 watts. The weightlifter developed 2,658,25 watts. That's equivalent to 3,6 horsepower. In other words, he did the work of more than 3 horses in 1,2 seconds. You can find out how powerful you are by running upstairs as quickly as you can. Measure the height of the staircase and ask a friend to time how long it takes you for you to run from the bottom to the top of the stairs. Oh, I didn't tell you that we need to know your mass as well to do this calculation. Follow this calculation for Mr. X and repeat it to find out how much power you developed. Mr. X has a mass of 80 kilograms. He ran upstairs 3 meters high in a time of 5,4 seconds. His power is calculated by the work done divided by the time taken. The work done is equal to his change in gravitational potential energy. Power equals mass times acceleration due to gravity times height divided by time. Substitute the values and calculate the answer, and we get 435,56 watts. When an object such as a car is moving at a constant speed, its motor is working all the time to keep it moving at that speed. So the engine is developing power to keep the car running. We're going to derive a special formula for these types of situations to find out the average power of the object moving at constant velocity. Power is equal to work done divided by time. The work done is equal to the force applied by the engine times its displacement in the direction of the force. That is, work done is F times delta x times cos theta. But the car's average velocity is equal to delta x divided by the time t. And theta is 0 because the force on the car is in the same direction as its displacement. The average power is equal to the force applied times the average velocity. Remember that this equation only applies to objects traveling at constant velocity. Let's put this formula to work. A car traveling at 20 meters per second along a horizontal straight road develops 66 kilowatts of power. What is the driving force of the engine? Power is equal to 66 kilowatts, which is 66,000 watts. The car travels at a constant velocity of 20 meters per second. We're looking for F, the driving force of the engine. Because the car travels at constant velocity, we can use the formula average power equals force times average velocity. Substitute the values and calculate the force. And we find that the driving force of the engine is 3,300 Newton. We have covered the definition of power, and its formula P is equal to W divided by T. We've also covered the use of the formula P is equal to F times V when the velocity of an object is constant. In the last lesson, we'll tackle a few more questions on work, energy, power, and the work-energy theorem. Meantime, power to you as you work through these lessons.